Hello, good people, and welcome back. So, in the last video, we had a lot of fun working on this and getting us started, and we were able to do really good in essentially modeling security prices, right? So we could essentially say security price at some point in time t would be equal to the security price today multiplied by the exponential of our expected rate of return minus 1/2 of our volatility multiplied by t plus a random shock that we introduced there, which is scaled by the standard deviation. That's what we had there. What we want to do next is we want to use that information in order to infer the payoff of the option. You remember the steps: 1, model security price; 2, use security price to infer payoff; and 3, discount the payoff. So in this case, we're actually going to do the inferring the payoff and discounting the payoff at the same time, and hopefully we can come up with the same thing as the traditional Black-Scholes was able to come up with early on. And so this is essentially what we're going to be doing. The first thing that we are going to do is remember or recall the key elements, the key findings that we had from the last video. And the very first finding that we had from the last video was the following. We remember that we said that DST, that's our very first finding, was equal to mu. Let's use R, because we're working with the short time interval. And remember, when you're working with longer time interval, you can use mu, which is the expected rate of return, or you can use R. It really doesn't matter. It really doesn't matter here, just yet, right? And the reason it doesn't matter here, we could use mu or R, is because we have not introduced the notion of no arbitrage yet, right? Because if we are going to vary an option, we are going to be talking about possibility of arbitraging the model that we are developing here. And so what we want to do is we want to ensure that arbitraging is not possible for the model that we are building. And the way we introduce the no arbitrage is to say that if you're going to use this, you should earn essentially the risk-free rate of return on your investment. And so by doing that, we're essentially saying that the required rate of return is equal to the risk-free, which is why I want to use R here. And so I'm going to use R or the risk-free here to model this from now on, just because I'm building into this the no arbitrage condition that we have to have here to make sure that our model works and doesn't get violated in any way. In the absence of arbitrage opportunity, you remember that you're earning the risk-free rate of return on your investment. If there are arbitrage opportunities, you're earning, say, more than the risk-free, your expected rate of return. So that general form of ST that we had here was just, in a way, not accounting for the no arbitrage condition. Here we're building in the no arbitrage condition, so we can use the risk-free rate of return from now on. You may hear this little sound or scream in the background here. Is because my daughter is all the way in the back, and she is a little over 9 months old now. And she doesn't listen to me when I say don't scream when I'm recording. So I'm sorry about that if you can hear those little sounds there, but nothing I can do about that. Hopefully it's not too much to distract you. All right, so let's get back to work here. We remember that we had DST, that was the change in stock price that we modeled earlier, and we said it was equal to the required rate of return. And in this case, because we're building no arbitrage, we say that's equal to the risk-free multiplied by the stock price T multiplied by DT. To that we added a random shock, right? And that random shock was scaled by the standard deviation ST, and we had DBT. That was the first thing we had, and we want to remember that. That's why we want to keep that close. The second thing we found was that ST could be modeled as S0 multiplied by the exponential of that what we had there was r minus 1/2 of the variance, and that's going to be squared here multiplied by t, and to which we added sigma, and then we had the dbt here. Okay, so that was actually, no, that was not dbt, that was bt, because we had that change. Okay, let me do a capital T here. So this is what we have. What else do we have? You remember, I want to keep that close. We remember that bt was said to be able to model as the square root of t multiplied by our Wiener process. Okay, and you remember that our Wiener process was normally distributed with a mean of 0 and a standard deviation of 1. This is going to be important because we are essentially, you'll see a little later, we're going to be using probabilities here in a second. So the first step was modeling stock price. Check, we did that. Now second step is use the stock price in order to infer the payoff of the option. And so let's do that just now. We have an option that's written here and expires here at time t. And the payoff of the option is always going to be equal to the maximum. Let's use a call. Actually, yes, we're going to work with the call. And it's going to be equal to the maximum of the stock price at time t minus the strike price k, or 0. That's going to be the payoff of the option, and we always know that. We needed to know what ST is going to be able to say what's that maximum, what does that maximum look like. Okay. And the call option, if it is not variable, and it's going to be equal to 0. So the call option, the payoff really is going to be equal to, at this point here, the call option is going to be either ST minus K if ST, let's write that somewhere else. So the call is going to be equal to ST minus K if K ST is greater than K. That's what we know. Or it's going to be equal to 0 if ST is less than K. Right? So if the option is in the money, the payoff is the difference between the stock and the strike price. If the option is out of the money, the payoff is equal to 0. That's what we know. But how do we know that the stock is in the money, and how do we know that the stock is out of the money? Well, we don't quite know that, which is why we want to use probabilities. And so there's going to be a probability that's associated with that the stock price is above the strike price, and let's call that P, and that's going to be the probability that the stock price is greater than the strike price, and this is also going to be the probability that the stock price is less than the strike price. So what is our payoff? We have the probabilities and we have the outcome, so our payoff at time t is going to be a weighted average of these values, right? So what we're essentially going to have is we're going to have the following. Our payoff at time t is going to be equal to the probability that the stock price is above the strike price multiplied by the payoff in that case, and that payoff in that case is going to be equal to ST minus K, plus the probability that the stock price is less than the strike price, and the payoff in that case is 0. That's what we have. That's the payoff that we have. Now this is always going to be 0, so we can essentially forget about this portion. So our payoff again is going to be equal to the probability that the stock price is above the strike price multiplied by the difference between ST and the strike price. That's going to be the payoff at time t, and we need to discount that payoff, so we're going to multiply by the exponential of minus RT. And remember, R is our risk-free rate of return, right? And you know why we're using the risk-free rate of return here. So it's going to be exponential of RT, and we've discounted that. In that case, this value here would be equal to our call option value. This is how simple Black-Scholes model, option pricing model is. That's all there is to it. Now, what is stock? What is ST? We know what ST is. Okay. The trick there is really just going to be to find the probabilities. That's all we need to do now. And how do we do that? It's actually really simple and really fun to work with here. So let's get rid of those parentheses a little bit. Our call option value would therefore be equal to the probability that the stock is above the strike price multiplied by ST, right? Because we multiply that by that and by this, multiplied by the present value factor RT, and we do the same with the present value factor here, and then we do minus the strike price multiplied by the present value factor, that's RT, and then we multiply that also by the probability that the stock price is above the strike price, which is P ST greater than K. This is going to be our call option value according to Black-Scholes option pricing model. Alright, so we have two things to do here. The first thing is to say, what is this value here? What is this value here? And what is that value here? And then we do 1 minus 2. That's all we need to do. Alright, so how do we find... let's start with 2. 2 is a lot easier than 1. So let's start with 2 and we'll find out exactly what 2 is. Okay. So 2 tells us that we need to find the strike price, present value, and then we multiply that by the probability that the stock price is above the strike price. Okay. And so how do we do that? Well, we know what ST is is, and so let's use this. Probability that ST is above the strike price is also equal to the probability that, what is ST? ST is S0 exponential of, speak there, exponential of, remember what we had here. We had R minus 1/2 of sigma squared. We had T plus sigma, and we had BT. That's what we had there. And we want that value, because that's ST, we want that value to be greater than the strike price. Now, we don't really see how we're going to do this just yet. Because we're working with the exponential there, that's not clear enough. Let's get rid of that exponential, and we're going to get rid of the exponential by taking the log of both sides. So that is really equal to the probability that, I'm going to use the big brackets now, we have the log of S0 plus R minus 1/2 of variance multiplied by T plus sigma BT. And we really what this is me doing the log of this whole term here, right? And the log of this whole term, because this is constant, S0 is constant and it's outside of the exponential, I have to take its log alone, and the product of two logs is equal to the product of the log of a product is essentially equal to the sum of the logs. That's what I would say. So what am I saying here? I'm saying the log of xy is equal to the log of x plus the log of y. And so if x is equal to S0 and y is equal to the exponential of all of that, we're going to have the log of S0 plus the log of the exponential of all of that, which is whatever is up there. And we have the log of S0. That's what we have here. Log of S0, and we have the exponential value there. And we want that to be greater than the log of the strike price. That's all we have there. All right. How do we handle this from this point? Well, the only thing that really changed, because everything is constant, right? The probability of having a value a constant is just really zero if you're working in continuous time. And so in continuous time, the probability of having an exact value is equal to zero. The only random variable that we have there, which it can change, for which we can find the probability, is bt. So we need to isolate bt, which is our random variable. And how do we do that? Well, we simply say this is going to be equal to the probability of having the following. We're gonna isolate bt. So we're gonna say bt here is gonna be greater than we're gonna have the log of k. We're gonna subtract the log of s0. We're gonna subtract the whole term there. So we're gonna do minus r minus 1/2 of sigma squared multiplied by t, and then we're going to divide all of that by the standard deviation. So we're going to divide this by the standard deviation, and what we're going to have is what we have there, bt. Now bt follows it's a Brownian motion. We don't really know what the distribution there is going to be. However, we know that a Brownian motion is just a general form of a Wiener process. And so if we say that bt is going to be equal to z divided by multiplied by the square root of t, you remember what we had earlier there, right? You remember this. If we say that bt is equal to that, and we divide the two bt by the square root of t, so if we do bt divided by the square root of t, we essentially have a Wiener process. And we know what the distribution of the Wiener process is. We know it's normally distributed. So we know essentially that we can find the probability when we know what the distribution is, normal distribution. And so what we're going to do here is we're going to divide both sides by the square root of t. So we're going to divide this by the square root of t, which means that we have a Wiener process, and we divide by the square root of t, and we have a Wiener process essentially. So because we divided by the square root of t, we know that this probability function is a normal probability function. So we're going to call this, that's going to be equal to the normal probability function of bt divided by the square root of t. So let's do that. Let's do bt divided by the square root of t. That's greater than the log of the strike price minus the log of the stock price minus r minus 1/2 of the variance, and then we have t, and we divide that by standard deviation square root of t. Now you remember also that the log of x minus the log of y is equal to the log of x divided by y. That we know. But our normal probability function really does this. It says that, so when you look at the z table, the standard normal distribution function, because you know that the Wiener process follows the standard normal distribution, right? So we're going to use the standard normal distribution. What do I mean by standard normal distribution? If we go back here, you know that your Wiener process has a mean of 0 and a standard deviation of 1. That's your standard normal distribution. You have a table that gives you the probability for the standard normal distribution, and that's your z table essentially. But your z table really gives you the probability of having a value that is of observing a value that's less than your z score essentially. And so what we want to do is we want to have a less than or equal sign here, not a greater than sign. And so to do that, what we're going to do is we're going to have a we're going to convert that, we're going to multiply both signs by -1. And so what we're going to do is going to say n of n of bt, which is divided by the square root of t, is less than or equal to the negative of that value, which is minus minus the log of k plus the log of S0 plus the difference between R minus 1/2 of the variance multiplied by t, and we divide that by the standard deviation square root of t. I keep getting those, and then we have that. Okay. This can be read directly from our normal probability table. And this, what we were working here was just trying to find what the probability of P greater than the strike price, the stock price greater than the strike price there. We substituted ST by its value. We took the log of both sides in order to get rid of the exponential function. And we divided both sides, and we isolated BT because that's the only random variable that we have there. Everything is constant, everything is known, can be calculated. Essentially, the only random variable is BT, and we want the probability that the random variable is essentially above the threshold. So the shock essentially is large enough that the change, the random movement is large enough that the option expires in the money, essentially, or the strike price, the stock price is greater than the strike price. So when we divided both sides by the square root of t, we were able to identify exactly what is the distribution of this term here, because the Brownian motion divided by the square root of t is a Wiener process, and we know that the Wiener process is normally distributed. So instead of writing p as if we don't know what that probability distribution function is, we're going to write n because we know that it's normally distributed, and it has to be greater than this value that we have here. Now, to read that clearly from the normal probability table, we need to change the sign. And to change the sign, we need to multiply this by -1. And so we multiply that by -1. We have minus the log of k plus the log of S0, and then we have that whole term there. This is just the probability that the stock price is above the strike price. Okay, and so what does that give us? Remember, 2 was the strike price present value multiplied by the probability that the stock price is above the strike price, and we found this value here to be equal to the probability that the normal distribution function, so that we have the bt divided by the square root of t, that is less than which is minus, actually let's do this right, that better, bt divided by the square root of t, which is less than the minus the log of the strike price plus the log of S0, or plus R minus 1/2 of the variance multiplied by t. We divide the whole thing by standard deviation square root of t, and we have that. Let's rewrite this term here. That term there is going to be equal to the log of S0 divided by k plus R minus 1/2 of the variance multiplied by t divided by standard deviation square root of t. And let's call that the d2. And so the probability can be read directly by reading the normal density, the normal probability table for d2. So we can essentially say that 2 is going to be equal to k present value multiplied by n d2, and that's essentially what we have here. And d2 is going to be equal to this value here. Now you're starting to see your Black-Scholes stick shape. So what do we have? We said that the call value was equal to the probability that the stock is above the strike price multiplied by the stock at that point in time present value, and to that we need to subtract 2, and we just found out that 2 is equal to the strike price multiplied by the present value factor multiplied by n d2. So we're done with the second component. We need to clarify what this first component really is all about. we are doing good here because we have 2. That was 2. We done with that, and we need to find what 1 is. 1 is a little trickier, but it's doable. How do we do that? 1 tells us that we have the probability that the stock price is greater than the strike price, multiplied by ST, multiplied by the present value factor as RT. And we need to simplify this. The problem with this expression though is we could use the same approach that we used earlier, right? We could just plug in the probability value here that we found earlier, call that ND2, and multiply that by ST present value. But you still have ST here, right? So we've not made particularly good progress if we did just that. And so we're gonna do something a little different. We're gonna plug in ST here. We know what ST is. We know how we can model ST. ST is going to be equal to S0 exponential of R minus 1/2 of the variance T plus sigma BT. That's what we're going to plug in there. And then we're going to go through that process and we'll see what we get. So what do we have? Let's start, instead of dealing with this, let's put this aside first, and let's work with this term here. Okay, so let's just take care of this term here. What essentially is that term that we have there. We're going to start by substituting ST for its value. So ST, that's going to be equal to S0 exponential of, you remember what we had here, that was R minus 1/2 of variance, and then we had T here, and we had sigma BT. That was ST, and then we multiplied this by exponential of, let's do this, let's multiply this by the exponential of RT minus RT, that's the present factor. Now you also remember that when you're working with exponential functions, the product of the exponential is exponential of the sum, right? So the exponential of x, exponential of y is equal to the exponential of x plus y, which means that we can split this term here that we have here into several components. Let's do that. So that's S0. We have the exponential of, now let's get rid of the brackets. That's going to be RT and minus 1/2 of sigma squared T, and then we're going to have plus sigma BT, and then we have exponential of minus RT. Okay. What else can we do? You remember this expression that we have, x and y. Let's call this x, let's call this y. And what does that give us? It says S0 is equal to the exponential of RT, that's e of x, multiplied by the exponential of minus 1/2 of sigma squared t plus sigma BT, and that's y. And then we still have this term here, so that's going to be exponential of minus RT. Okay, so we know that the exponential of minus x multiplied by the exponential of x is going to be equal to the exponential of minus x plus x. That's going to be equal to the exponential of 0, which is going to be equal to 1. Essentially, they cancel each other. So what do we have? We have my exponential of RT and exponential of minus RT. And if this is true, that's going to be equal to 1. So the product of those two is going to be equal to 1. Ultimately, we have S0 exponential of minus 1/2 of sigma squared t plus sigma BT. And so that's going to be equal to this term that we have here. And that's why we needed to do that, because that gets rid of the present value factor there for us. The problem with this though, and if we add a probability, we would multiply this by the probability that the stock price is in the money. That's going to be S T that's greater than K. That's the probability that stock price is in the money. That's ND2. That's essentially what we would have. The problem with this, and the reason we are not going to use ND2 directly here, is simply because we have this BT here that is still a random variable. So although we can find the probability here, we're still going to have a random variable, which is not going to help us in computing the call price, right? Because we cannot have the call price as a function of a random variable that is BT, which is the random shock. And so what we want to do is we want to find a way to get rid of that BT there. And so the way we're going to do this is by using another theorem that's called the Kirchhoff theorem. That's the I think that's how you spell Sanoff. That's the theorem. And in a nutshell, what the Kirchhoff theorem tells us is that if you have a Brownian motion B, let's call that B prime T, and the Brownian motion B prime T is equal to a Brownian motion that you know, that's BT, that's scaled by a factor that's sigma T. You can essentially model this, or you can find the first derivative of your Brownian motion with respect to the new Brownian motion, which is this value here, with respect to the old Brownian motion, and that derivative is going to be equal to, so the derivative of the new Brownian motion with respect to the old Brownian motion is going to be equal to the exponential of sigma BT, which is the old Brownian motion, minus 1/2 of the variance multiplied by T. This is the theorem that we're going to use to simplify this process. Okay, and the way we're going to use this theorem is to say that we're going to define, in a way, a new behavior of a stock price that doesn't follow the old Brownian motion, that doesn't use the old Brownian motion, but rather use the new Brownian motion. And what am I saying? What I'm saying is, if I can model stock price as a function of the new Brownian motion as follows, I can say that BT is equal to the new Brownian motion V by T plus sigma T. If I can do that, and I can replace this BT in here in S0 in this value of ST, if I can replace that by this value here, I won't have to worry about this term, because then I could be using this theorem, and I could just be working just like what I did earlier in finding ND2. What does that mean? And that's why I said this is a little tricky. What I'm saying here is that instead of writing P of ST greater than K multiplied by ST exponential of minus RT, this would essentially, for our purpose, be equal to the following. It would be equal to a P ST greater than K here multiplied by S0 multiplied by S0, and the reason it would be that is because this term here would be equal to 1. And the only reason that term would be equal to 1 is because this ST that we have here would be expressed as ST would be equal to S0 exponential of, and then we're going to have R minus 1/2 of the variance multiplied by t plus sigma bt, but this is going to be the new bt. Okay, a function of the new bt anyway. And the function of the new bt, remember what we the Brownian motion that we had, and that would be b prime t plus sigma t. That's what we would have. So the theorem here allows for us to say that instead of writing bt as we normally have, which is the Brownian motion, instead of writing it as we normally have, we're going to express it as a function of a different random process that from which we subtract the sigma t. And when we do that, we can find bt, which is equal to the new Brownian motion process plus sigma t, and that's what we have here. And so when we substitute that, this expression that we have becomes this, because this term then turns to be equal to 1. Okay, and so what do we have? We have the following. St is therefore going to be equal to S0 exponential of, then we're going to keep that here, r minus 1/2 of sigma squared, and then we have t. And then what we're going to have here is we're going to essentially include the b prime t that we have here and the sigma t. So it's going to be plus sigma t b prime t. Let's do that. Let's b prime t plus sigma squared multiplied by t. And all I'm doing here is multiplying this by that and multiplying this by that. Okay, so let's go to the next page and do just that. Remember, st we found equal to S0 exponential of r minus 1/2 of sigma squared multiplied by t. And we also have, do that, plus sigma b prime t. That's the new process. And the new process is just a Brownian motion, right? It's a normal Brownian motion, but it's a scale Brownian motion. And so once we have that, we add sigma squared t. Now let's get rid of the brackets, just like what we did earlier. So S0 exponential of, get rid of the bracket here, that gives us RT minus 1/2 of sigma squared t plus sigma Brownian motion t plus sigma squared t. And so what do we have? We have minus sigma squared t, 1/2 of sigma squared t plus sigma t. That gives us sigma squared t minus 1/2 of sigma squared t. That gives us 1/2 of sigma squared t, right? But this comes to the plus sign because this is essentially 2 times that. So S0 is going to be equal to the exponential of RT plus sigma 1/2 of sigma squared t that we have here plus sigma in the new Brownian motion. Now let's put the t back to where it was earlier. So that gives us S0 exponential of, so because what I'm saying is let's put the bracket back. That's going to be r plus this time 1/2 of variance, and then we have t, and plus sigma b prime t. That's our S0. And this is what we want to be greater than, that's our ST, and this is what we want to be greater than the strike price. So we want this to be greater than the strike price, K, and we want to find the probability of this value. Just like what we did earlier, we're going to take the log of both sides. So we're going to take the log of both sides, that's going to be the log of S0, plus we're going to have R plus 1/2 of variance, and then we have T, and then we're going to have sigma, and we're gonna have the new Brownian motion process B prime t. We want that to be greater than the log of the strike price. We have our probability factor, the probability here. And what we want to do next is, because this is the only random process, we want to isolate it. And the way we're going to isolate it is as follows. We're going to move the everything else on the other side. So we're going to have the new Brownian motion process bt prime, which has to be greater than the log of k minus the log of s0 minus, and what we're going to have is r plus 1/2 of sigma squared, and we have t here. Remember, because we're working with the Brownian motion, we want to get rid of the Brownian motion to work with the Wiener process, which is normally distributed with a mean of 0 standard deviation of 1. And to do that, we're going to divide both sides by the square root of t. Oh, this is already divided by standard deviation because of the standard deviation. So we divide that by the square root of t, and we add the square root of t here. And this is what we will have. Now, this is a Brownian motion that's scaled by the square root of t, so it's a Wiener process, which means that it's normally distributed. So we need to have n here. Okay. Now, because the standard normal table uses the less than versus rather than the greater than sign, we multiply the by -1. So we essentially have n of b prime t divided by the square root of t, that is less than the negative sign of that, which is minus the log of the strike price plus the log of the stock price. Let's write that better. Log of the strike price plus the log of the stock price, plus, and what we're going to have is r plus 1/2 of the variance multiplied by t, that is divided by standard deviation square root of t, and that's what we have. Now we could rewrite this term here as follows. We're going to have log of s0 divided by k plus, and then we're going to have r plus 1/2 of the variance, and then we multiply that by t, and we divide that by standard deviation square root of t, and then we're going to call that d1. And so our n of d1 is going to give us that. And you remember that when we made that assumption, we said that this term here was going to be equal to that. And so when we have the probability term, we multiply that by s0. So we need to multiply this by s0. And so what do we have? We have our call option that's equal to this s0 and d1 plus what we had earlier as 2, which was this, and it came with a negative sign, I should say. So it's going to be minus the strike price present value, and we multiply by n d2. And this is your famous Black-Scholes option pricing model expression for the pricing for call. Now n d2, you remember, is the real probability that st is greater than k. That is how we read nd2. Now we don't really read nd1 as the probability that the stock price is greater than k, because we made a slight modification on the process, the random process that we work with here. Because we use a different random process here, we want to be careful on how we interpret nd1, and we're going to talk about that here in a second. But for now, this is what we have. We have a call option value is going to be equal to the stock price multiplied by a probability nd1 minus the strike price multiplied by probability nd2. And nd2 was straightforward. ND2 is clearly the probability that the stock is going to be exercised, or the probability that the stock price is going to exceed the strike price. ND1 is very similar, but ND1 has been tweaked a little bit to be able to simplify the process for you, to simplify the math for us. That's why ND1 is not directly a probability that the stock price expires in the money, essentially. Now, note that I keep saying that ND2, which is what we have here, is the probability that the stock price is exercised, right, or is greater than the strike price. In ND1, this is true. The ND2 is true only if we are in the risk neutral world. Right? And the reason for that is because you see how we keep using this risk-free rate of return here. Is because by using the risk-free rate of return there, we are removing any arbitrage opportunity, any possibility of arbitrage. And so if we cancel the possibility of arbitrage, we are essentially in a risk-free world or a risk-neutral world. And in that context, with no arbitrage, ND2 would be the probability that the option expires in the money or the option gets exercised. Now, to understand really what ND1 is, what we're going to do is we're going to continue this process. We're going to actually find the future value of the call. The future value of the call, you remember, is the payoff of the option at expiration, right? Because you remember what the process we had. The process that we had was one, model the price, two, infer the payoff, and three, we had to compute the present value of the payoff. And that was how we found the call option price. That's essentially what we did. And so if we compute the future value of the call, we would essentially find the payoff, right? And that would be the payoff at expiration. So let's do that. If we did that, we would say the call option value, or the future value of the call, let's do that. So it's going to be call, and we multiply it by exponential RT to find its future value. That would be equal to S0 and D1 multiplied by ERT, just the future value that we added here as well. So it's going to be ERT here, and we do the minus the strike price, and then we do minus ERT multiplied by RT, and then we have ND2. Now you remember what we had here, right? Whenever we multiply the exponential of minus RT by the exponential of RT, we get 1. So the future value of the call, which is really the payoff of the option, is going to be equal to S0 and D1 future value minus, and what we have here is going to be the strike, so K and D2. Do you remember, however, that the payoff of the call is supposed to be equal to ST minus K? And so the way we're going to go about interpreting ND1 is not just looking at ND1 on its own, but looking at ND1 in terms of the future value of the underlying. And so ND1 would be a probability that multiplies the stock price, or that multiply the future value of the stock price at the risk-free to obtain the future value of the underlying. And that's essentially what we have. So this component here, which is S0 multiplied by ND1 future value, that is the expected value of the stock price at expiration of the contract, which is at maturity of the call option, or the expiration of the call option contract, remaining in that world that we have, which is the no arbitrage world or the risk neutral world. And that's essentially what we would have. And that would be how we go about looking at ND1. And I know ND1, the interpretation of ND1 is really tricky. And the only reason it's tricky, and the only reason it's not as simple as that of ND2, is because of the modification or the change that we made earlier when we changed the random process. Because on the one hand, we used the random process BT when we were computing the probability ND2. We cannot use a different random process, compute the probability ND1, and say those two values are equal to each other. And that would not be true. So the true probability that the stock price expires in the money or the stock price get exercised is going to be equal to ND2. And the interpretation of ND1 is going to be a function of that future value of the underlying. It's going to be in line with the understanding that the future value of the underlying at expiration is a function of ND1. Okay, I know that's tricky, and I hope that somewhat makes sense for you. Another way of looking at this is to essentially work something a little different. And by that, what I mean is, if we say that if we remember that the call option value is equal to the stop price, and then we have ND1 multiplied by minus the present value of the strike multiplied by ND2, and if we factor out that present value from both sides, let's say we factor out this term here that we have from both sides of the equation, that's going to be this term here. If we factor out that term, what do we have? We have exponential of minus RT multiplied by ND2, and what we're going to have here is going to be S0 multiplied by ND1. But then, because we are taking away the exponential function here, what I want to do is I want to multiply this by the future value. So it's going to be exponential of RT. Doing that would multiply the ERT here, E minus RT that I have here, to make 1. So when I open the parenthesis, I'm going to multiply this term here by that term. That's going to be 1. I'm going to get back to S0 ND1. And then I'm going to divide this by ND2. And so if I did that, I would essentially be doing S0 ND1 exponential minus RT exponential of minus RT, and we multiply by ND2 and divide by ND2. So this here would be what is out of the bracket here, and this here would be what is in here. So I'm just multiplying the two, and when I'm multiplying those two, that cancels that, this and that multiply to be equal to 1, so I just have SND1. That's all I have there. Okay, so I factor out this value there, and because I took that away from here, I'm left with the strike price, and that's essentially what I would have there. And so if we did that, we would still have the call option value. That would still be equal to that, but I would be looking at this ratio here that I have here in the bracket. Remember, that's the future value of an underlying, and that is divided by the probability that the stock price gets exercised. And so the ratio of S0 multiplied by ND1 future value, should have that right as well, future value divided by ND2, really that ratio here is the future value of the underlying, or the expected value of the underlying. Again, whenever we talk about that expected value, we need to remember that we are working in a risk-free world, or we are working in a no arbitrage world, and so we need to be clear that is the future value of underlying in that world, in the risk-free world or in the no arbitrage world, conditional on the fact that the option gets exercised or the option expires in the money. So that is what this term would be. It would be the future value of the underlying in that world conditional on the exercise of the option. All right, that's another way of looking at what ND1 serves, the role that ND1 serves in this context, because in doing so we could still be using the call option value. And so what do we have? We have essentially the present value of the future value of the underlying if the option is exercised minus the strike price, which is in a sense what the payoff of the option is if the option is exercised, multiplied by the probability that the option actually gets exercised, and then we find the present value. That's how we interpret the call option value. And so some just use this expression as it is here, others prefer to use what we have up here. And they are identical. The second expression that we have here simply helps in explaining clearly what the role of ND1 or that probability that we have there. Okay. All right, so that wraps it up for us in the derivation of the Black-Scholes option pricing model. And so what we're gonna do next is we're just gonna go over the slides and just summarize the slides, and then we're gonna revert back to in the next video to doing some practice on all of this. I hope this derivation was meaningful. I hope at least that it helps you understand the power of Black-Scholes option pricing model, because this is so beautifully constructed that it could be used in a variety of contexts. It could be modified to account for dividends. For example, in this case, we're working with a dividend as an assumption that we have not even mentioned so far. I don't think we're working with a non-dividend paying stock, and we're working with an European option, right? Because we are assuming that we are holding the option all the way to maturity. That's why we're using the payoff at maturity and we're discounting it. Okay, and so if we're working with an American option, we may not hold the option all the way into maturity. So that needs to be tweaked a little bit to account for the possibility of exercising the option before maturity, which is going to affect ND2, which is going to affect ND1, and if dividends are paid, that's all that's going to do is affect the stock price ST, and that's easy to address. All right, so let's go back to the slides and see what we have. We're still in the slides here, so let's see what we have here. The Black-Scholes option pricing, the Black-Scholes assumptions, random walk assumptions. So we consider a stock price as in a short period of time that we call delta t. We look what delta t is. The return on the stock is delta s divided by s, and that is assumed to be normal with a mean mu delta t and a standard deviation that's equal to sigma square root of t. That's very close to what we described earlier, but we looked at the log normal distribution of security prices, and we'll talk about that some more in a little bit. So if mu is the expected return on the stock and sigma is the volatility of the stock, that is, if mu that we have here is the expected rate of return and sigma is considered to be the volatility. The log normal property of security prices is simply the assumptions that the log of ST, which we looked at earlier, is normally distributed with the mean of equal to the log of S0 plus mu minus sigma squared divided by 2 multiplied by t, and we saw that, and the standard deviation is equal to sigma square root of t, which here means that the variance would be equal to sigma squared t, and so that's going to be your variance. And we've seen that earlier when we talked about log normal distribution of security prices, and that was, if I can find that up all the way up here, so that was somewhere Up here we talked about the log normal distribution of security prices. We said that the log normal distribution is so the log of ST follows the normal distribution with the mean of log of S0 mu minus 1/2 of variance T, and a variance that's equal to sigma squared T. Here that means that the standard deviation, which is the square root of a variance, is sigma square root of T. That's essentially what we have there. And I think we actually mentioned the sigma square root of T when we talked about Black-Scholes, not Black-Scholes, when we talked about binomial, and we said that U was raised to the exponential of sigma square root of T. That really is the standard deviation of the log normal distribution of ST. Now, because the log of T of ST is normally distributed, ST is going to be log normally distributed, and we saw that earlier as well. And so the log normal property is that the log of T is going to be normal distributed. Your book uses phi or phi in French to say normal distribution. Generally is n. So normal distributed with the mean log of S0 plus sigma plus mu minus sigma squared divided by 2 multiplied by T, and a variance sigma squared T. Or the log of the ratio is normally distributed with the mean that's equal to mu minus sigma squared divided by T multiplied by T, and the variance that's equal to the same. And the reason the variance doesn't change is because the log of ST that we have here is a constant, so that really doesn't affect the volatility here, but it does affect the mean. And phi here is just a normal distribution. M is the mean, V is the variance. So the first term here is always the mean, the second term is the variance, and the phi there is just to say that it's the normal distribution. We use N in our description earlier. Alright, so if security prices are log normally distributed, they would look something like this, and the expected value of the stock price would look something like this. So it's going to be the future value of the stock today raised to the power of RT or mu T, and the variance is going to be equal to S0 squared, the exponential of 2 times mu multiplied by the exponential of sigma squared T minus 1. This is easy to show because you know that the expected value of the variance of ST is going to be equal to the expected value of ST squared minus the expected value of ST, that is going to be ST, expected value of ST, and then we have that squared. And so by applying this, we would essentially find that. Alright, our expected return properties. Here the expected value of the stock price at time t is simply the future value of the stock price at mu t, and we saw that the return in a short period of delta t is going to be equal to mu delta t, but the expected return on the stock with continuous compounding is really going to be equal to mu minus the sigma squared divided by 2. And the reason for that is because when you're working with geometric Bayesian or geometric return, you know that the geometric return is always going to be lower than the arithmetic returns. And so when you're working with a short time interval, you're really just looking at the arithmetic return. That's what this is going to be. But the geometric return is truly going to be that. And that's why that's an implication of why, or a reason, or one reason why you are using this term here, right? And we showed essentially how it came about. There is a volatility component that goes to subtract the expected rate of return when we do the math. And this came up when we essentially worked with our log normal distribution with what we had here. So you remember earlier when we were essentially, when we use ethos lemma, if you go back to look at where we talked about ethos lemma, and we use the geometric polynomial motion in ethos lemma, and we use the log of st to model the log of st, or the change in the log of st. That's exactly where that risk rate of return was affected by, or got linked really with this value here. I think I can go back all the way up there and essentially show you how that came about. So if we go back here, we would have, I think it was somewhere here. Okay, so at this point we were still working with mu. So if we go back here, I'm going to use this color. We were still working with mu as a standalone return. Okay, but because of this change in time, this dt is connected with that dt, and we have this volatility here, we find that the true return is reduced by this component. So we have dt here and we have dt here, so we factor out the dt. We find that this is the net return. This is the true return on your investment when you use continuously compounded return in this context. And that's different from the traditional arithmetic return that would only be equal to that. And the reason we are looking at this is simply because this really is just a constant, right? So that it goes nowhere, and the only place it can go is not to reduce the random variable, but to reduce the return that you have there. All right, and so this reflects the difference between the arithmetic return and the geometric return. We talked about that, and remember that the geometric return is always smaller than the arithmetic return. And as a rule of thumb, you can think that the geometric return is smaller than the arithmetic return by a factor of variance divided by 2. All right, so what about the volatilities? So with respect to the volatilities, we know that the volatility of the asset is just going to be the standard deviation of its continuously compounded rate of return in the given year. So we have the return over the period, and we just compute the standard deviation of the return. So and that's something that you may want to remember, is that whenever we talk about volatility in this context, we really mean standard deviation, not variance. Okay, so volatility here refers to standard deviation, not the variance, and usually it's referring to the standard deviation of the returns of the return series, not the standard deviation of the price series. And the standard deviation here is going to be equal to the standard deviation of the return over a period of delta t is equal to the standard deviation multiplied by the square root of delta t. This is just a byproduct of something that we've been working with so far. So if we go back all the way up here and we say the standard deviation over a 1-day period is given to us, the standard deviation over an n-day period is going to be equal to, so the n-day standard deviation is going to be equal to the 1-day standard deviation multiplied by the square root of n, and that's going to be the square root of the number of periods. And so if we want to work backwards, and we assume that we are given the n-day standard deviation, so if this is given and we needed to find that, we would essentially say that the standard deviation for the 1 day is going to be equal to the standard deviation for the n days. So it's going to be the n days standard deviation that's divided by the square root of n. Now I think your book uses something a little similar. So your book does something like this. It says the square root of n days, or the standard deviation for the n days period, is equal to 1 over the square root of n, and that's equal to the n day standard deviation. So it's going to be standard deviation n days multiplied by the square root of 1 is essentially 1. So it's going to be the square root of 1 divided by the square root of n. And so that is equal to, and that should be, you should write that here, the n day standard deviation multiplied by the square root of 1 over n. And I think that's what your book used if you are to find the standard deviation for the 1 day. And so if you're working with if you have the daily standard deviation and you want to find the annual standard deviation, if you have the daily standard deviation and you want to find the annual standard deviation, you multiply by the number of days in the year. And typically in practice we use the number of trading days. So n is typically equal to 252 days because we're using 252 trading days in the year. So the annual standard deviation is the daily standard deviation multiplied by the square root of 252. However, the daily standard deviation is going to be equal to the annual standard deviation multiplied by the square root of 1 over 252. And that's essentially what that down there referred to. So here we're told that if a stock price is at 50 and its volatility is equal to 25% per year, so that's our annual standard deviation. What is the standard deviation of the price change in 1 day? So you're given that would be the standard deviation for n days, which is 252 days, and you're asked to find the 1 day standard deviation, and you need to find that in dollars because you are given the security price here. And so how would you go about doing that? Well, the 1 day standard deviation is going to be equal to the n day standard deviation, which is the annual standard deviation that we have there, and we're going to multiply that n day standard deviation by the square root of 1 divided by the number of trading days. So in this case, our 1 day, our standard deviation 1 day is going to be equal to the 25%, which is the n day standard deviation. I'm going to use 25%, which is the n day standard deviation, multiplied by the square root of 1 over 252. And 252 is used here because we're working with the trading days, the number of trading days in the year. Essentially, that's how you'll find your 1 day standard deviation. Now, if you wanted to find that in dollar term, you will multiply that by 50. And that would give you your standard deviation of the security there. And really the way you see that is you know that this is going to be sigma square root of essentially t in years is going to be 1 day in years is 1 over 252. So it's going to be square root of t, where t is going to be equal to 1 day expressed in years. And if you multiply that by st, you see that this term is the random component, right? So when you have your dst is equal to st multiplied by mu multiplied by dt, and then to that you add st multiplied by sigma, and you multiply by dbt. Okay, and so you remember that when you're working with the Brownian motion, dbt that you have here can be expressed as a function of a Wiener process, right? And you know that the Wiener process is essentially standard normally distributed. So this really is equal to st mu dt plus st sigma. And remember, we're going to convert dbt, and we said that bt is equal to what was that? Square root of t multiplied by the Wiener process. And so what do we have? We have square root of t, and we're going to have the Wiener process. We call this the drift term, and this was a random term, and a random was a random variable that was scaled by a variance, a standard deviation. And so this would be the standard deviation that you're working with. That's what you're working with, that term here. And so in dollar terms, because this is a dollar change in the stock price, you multiply that by the stock price, and this is essentially what you have. In this case, you would simply ignore the DWT there, the DW that you have there. Actually, it shouldn't be DWT, not DT, because it changed the times as well. All right. So when you say the standard deviation, you think of this value here, and when you say mean, you think of that value, the value there. The nature of volatility, what do we have here? Volatility is usually much greater when the market is open. That's why you want to use trading days. For this reason, it is for this reason, time is usually measured in trading days. That's why you want to use trading days, not the calendar days. So you don't use the square root of 360 days in a year, 65 days in a year. You use 252 days because there are 252 days in the trading days in the year. All right. So how do we estimate volatility? We use historical data. So we take the observation of security price over a regular time interval. Usually you use a day, or if you use weeks, the time interval tau is going to be 1 week, and the week expressed in years is 1/52, and that's because we have 52 weeks in a year. And so we're gonna, and tau has to be constant, right? So it has to be a regular time interval that you're using here. And so you're gonna be computing the continuously compounded return for each time interval. So it's gonna be UI is the return, and our continuously compounded return is gonna be the log of the current price divided by the previous day's price, or the previous week's price in this case, because we're working with weekly data. With the return, those are the UIs. We're going to calculate the standard deviation of the returns. You know how to do that, and those are going to be your estimates of standard deviation. Now, because you're working with an estimate of historical standard deviation, and you're using essentially a sample, not a population, your standard deviation estimate is going to be whatever standard deviation you obtain divided by the square root of tau. And that's how you would obtain your estimated of standard deviation. Now, this is how your book characterizes it. But when you think about it, when you model security prices, you're saying, for example, in the case of binomial, you say S0 is going to be S up and S down, and you use a volatility going forward, right? You're not using a backward volatility. You're not using the volatility of past return. You're assuming a future volatility in modeling security prices. So in practice, people use forecasted volatility instead of using historical volatility. So that's something to keep in mind as well. So you can see people using method like Gauge or EWMA. So Gauge is a generalized autoregressive conditional heterostrict stochastic model, or the EWMA is the exponentially weighted moving average method to compute future volatilities and use future volatilities as the estimate of volatilities. So that's also something that's used very often. Alright, so what are the concepts underlying Black-Scholes? Option prices and stock prices depend on the same underlying source of uncertainty, and you remember that this underlying source of uncertainty really is our Brownian motion, also our Wiener process, right? So it's DVT or DWT. That's our source of uncertainty. That's the random shock that we are able to build into our model. So when we model security price, we use this. That's the shock that we use, and when we model option price, when we derive option value, we use the same value. Say they both are a function. So stock price and option price are both a function of the same source of uncertainty, the same shock. So we can form a portfolio consisting of stock and an option, which eliminates essentially the source of uncertainty. And so that's another way of building of coming about with Black-Scholes, and we'll talk about that here in a little bit, actually in another video. I'm going to come back to this in another video and showing you exactly how we use portfolio replication. That's very similar to what we did in binomial to derive the Black-Scholes option pricing. But in this case, when you do that, you're not really obtaining Black-Scholes call value or put value. What you're obtaining is the Black-Scholes partial differential equation. And I don't think your book even mentions the Black-Scholes partial differential equation, but just in case, by constructing a portfolio in order to eliminate the uncertainty in that risk neutral world that we've built, and in order to construct this function, this Black-Scholes option pricing model, what we are using is essentially an arbitrage scenario, right? A no arbitrage scenario. And when we do the no arbitrage scenario, you construct a risk-free portfolio that earns you the risk-free rate of return, and in doing so, you're eliminating uncertainty, right? Because when you have no risk, you have no uncertainty. And so that's what that refers to. By constructing a hedging portfolio, a hedge portfolio, you're able to get rid of this DWT or this DBT. But what you obtain there is the Black-Scholes partial differential equation. And what that simply is the value of the option. Well, it says that the change in the value of the option with respect to time plus 1/2 of the second derivative. That's a change in value of the option with respect to the security price as ST squared, and multiplied by S squared T multiplied by, I think it's the variance, that's the variance, and then we can add the value of the underlying first derivative ST, and that's going to be multiplied by R, that's the risk rate of return ST. And remember that this is derived from the idea that we have eliminated the uncertainty. So we are earning the risk rate of return here, not mu. And we're going to subtract from this R multiplied by the value of the option, and that's equal to 0. This is known, or this expression that we have here, is known as the PDE, so it's the partial differential equation for Black-Scholes. Okay, so setting up this hedge portfolio to result in that, and then you can use that to construct the value of the option using the value of that option, which is essentially what this value is. V here is. Maybe we can do that in a little bit. I think I'm going to show you perhaps in another video how you can put this together. All right, so the Black-Scholes formula is essentially comes up to the call option value is S0 ND1 minus the present value of strike price ND2. We talked about that. How do we generate the put value? Well, to generate the put value, we're going to start with the call value, and we're also going to use the put call parity. We're going to do that in a little bit. So this put value uses the put call parity, and that is essentially a direct result of what we had earlier. And D1 and D2 are exactly the same. Remember, the difference between D1 and D2 is essentially that for D1 we use a plus sign in here, and for D2 we use a minus sign in here. And D1 is going to be equal to D2 is going to be equal to D1 minus the denominator, which is sigma square root of T, which is the volatility. All right, so that's what we have here. And remember that when we say ND1, we're talking about a normal probability function, and that's a probability that is the probability that a normally distributed random variable with a mean of 0 and a standard deviation of 1 is less than. And you remember when it says less than, and that's why we had to multiply that term. So if we go all the way back up here, we had to have the less than sign here. That's why we went from here, multiply this by -1 in order to change it to a less than, so we could use the normal probability function. Essentially, that's what that's about there. All right, so essentially this would be your D1, and then you would have your probability, and you compute the D2, you have your probability there, essentially. Now, what are the properties of Black-Scholes? As S0 becomes very large, that's the underlying, the call tends to S0 minus the present value of strike. So the option gets to the call option, it gets in the money. So if the stock price increases, the call option is in the money, essentially gets closer to getting in the money, because ST tends towards S0, and then we have that with the respective probabilities, and P, which is the put value, tends to 0. So when the call is in the money, the put loses value on the same underlying and the same strike. As S0 becomes very small, the call value tends to 0, because S0 tends to 0, it's getting smaller, and then the put value increases. And the payoff of the put value is going to be the strike price minus the stock price, essentially. Now we use the present value factors here because we are looking at S0, right? So we need to discount the present value factor here. So what happens when volatility becomes very large? When volatility becomes very large, there is potential of the option becoming in the money. So the volatility is going to be positively related to the outcome of the options. So essentially, the probability that this is going to be increasing, the probability that the option is going to expire in the money is going to be increasing, and with that probability, the call option is going to be increasing as well. And the same with the put, depending on the sign of the returns that we have there. And what T is a constant. So what happens? I'm leaving this for you to essentially try to interpret. This is going to be a good practice to try to figure out how the standard deviation and I think we did that in binomial anyway. So you should be able to infer. This. Now our risk neutral valuation, that's essentially the assumption that we made when we said that in the no arbitrage world we are not going to use mu, we are instead going to use the risk-free, which is R that we have. So the variable mu does not appear in the Black-Scholes option pricing equation, and the equation is independent of all variable affected by risk preference, which is mu. Is the primary variable affected by risk preference, because that's the expected rate of return on the stock, and that is a function of risk. But if you're using a risk neutral world, or you're assuming no arbitrage, then you get rid of that. You're earning the risk free, so you're substituting mu for the risk free, and that's why Black-Scholes also use the mu there. And this is consistent with the risk neutral valuation principle. That's the no arbitrage rule that we have with Black-Scholes. How do we understand Black-Scholes? We talked about this. We can rewrite the call option essentially by factoring out the expected value, or the present value factor in ND1. And so this term that we have here, which is the ratio of the future value of the underlying, or the expected future value of the underlying, divided by the probability that the stock price expires in the money, or the probability that the stock price is exercised, that gives you an expected price of the underlying in the risk neutral world. That's important because of your assumption of no arbitrage, conditional on, or if that should be conditional on the option, the fact that the option is exercised. That's because it's divided here by the probability that the option is exercised, or the probability that the option expires in the money. If it expires in the money, it's most likely going to be exercised. So the strike price here is the strike price if the option is exercised as well. And the reason is because you have the ND2 that was factored out right off there as well. and you have to. So this, I want to be careful with this. The strike price is paid if the option is exercised. I guess that's what it is. I should be careful that if the option is exercised, and this is the K that. So if this is true and ND1's probability option is exercised, and this turns out to happen, that is that the stock price at that point is greater than the strike price. This is the price that needs to be paid. That's why this needs to be if the option is exercised there. So if we apply the risk neutral world valuation principle, we're going to assume that expected return on asset is the risk free, and we're going to compute the expected payoff from the derivative and discount it as a risk free rate of return. That's the process that we did, right? We assume that we are working in a risk neutral world. We model the security price as a function of that risk free rate of return. We infer the payoff, and we discount the payoff at the risk-free rate of return as well. Now, because you can value stock price that way, you can value essentially a forward contract in the same manner. So if K is the forward price and ST is the future value of the line, your profit or your loss on the forward contract would be the difference between ST and K. So that would be your payoff. And so the expected payoff on the risk neutral world would be that ST is simply the future value of S0. So that would be future value of S0 minus the futures price or the forward price. And the present value of the expected payoff would simply be equal to the present value factor multiplied by the payoff. And when you multiply, when you remove the brackets that you have here, so this times that times that, what you get is the forward price. The value of the forward price would be equal to the spot price minus the present value of the futures price or the forward price. That's very similar. That's exactly what we had earlier when we worked on futures and forwards, essentially. All right, implied volatility. The implied volatility of an option is the volatility for which the Black-Scholes option pricing is equal to the market price. At this point, what we're going to do is we're going to forget everything that we did with Black-Scholes. We're going to forget what we built. We're going to forget how we built it. And all we're going to remember is that the true price of anything is what people are willing to pay for it. Right? And so if the price, we can have the most fancy or the fanciest ever model that we can possibly build. At the end of the day, the price of an option in the market is what people are willing to pay for it, right? And so implied volatility says, well, what is that price that people are willing to pay for the option? Can we use that price and set that price equal to the Black-Scholes option pricing model and infer from that relationship what the volatility is has to be? So what should the volatility that is used in the Black-Scholes option pricing model be, so that the output of the Black-Scholes option pricing model is exactly equal to the market value of the option? That's the implied volatility. This is a one-to-one correspondence between the prices and implied volatility. Traders and brokers often quote implied volatilities rather than dollar price, and this is important. I think this is in line with the discussion that I had earlier on how it is that you model volatility. Because when you truly, I know your book says that when you to compute volatility, what you have to do is essentially use historical data. However, the Black-Scholes is a computes the value of an option for a future period of time. So the volatility out to be used there is really a future volatility. There are ways in which you can model future volatilities, not historical volatilities. Historical volatilities are fairly straightforward. There are ways in which you can model future volatilities using what we referred to earlier as Garch model or EWMA A model. But these are just estimates, right? So the true measure of volatility is unknown. And so sometimes, or not even sometimes, in the market, in practice, what happens is the price of the option that is quoted is really the implied volatility. It is people are willing to pay X amount for a call option. What that means is that this is what the volatility in the market should actually be. So the reverse engineer the Black-Scholes to solve for that volatility and present that volatility as the price of the option. So when you're trading options, you're really not buying and selling the future value of the underlying. You're trading the volatility of the underlying, and that's one way of looking at options. All right, so the VIX is that index of implied volatility, and so that is going to be the S&P 500 implied volatility from, and this graph is going to be from a period of January 2004 to 2015, and you see that the implied volatility is consistent with market condition, right? So when implied volatility rises, we are generally in period of financial stress. So when VIX is high, for example, in January 2009, that was we were just around to the late 2008 when we were with the market crashes in the mortgage crisis, and then we had the 2010, and then we had the 2012, and every time the volatility index increases drastically, it's a suggestion that people are pricing those options way too high, and if people are pricing those options way too high, it is because they are pricing the uncertainty in the movement of the underlying to be way too high, and that's because they think that the market's conditions are poor, extremely poor, and so risk is priced a lot higher. That's why the implied volatility spikes. So if people are willing to pay way too much for the value for a call option, the one metric that's going to capture that well is implied volatility, because it's going to shoot up, essentially. That's what that shows us. All right. How do you adjust for dividends? So far, we're working with European options. So European options on dividend-paying stocks are valued by substituting the stock price less the present value of the dividend into the Black-Scholes formula. So in the Black-Scholes formula, you have, say, a call is equal to stock in D1 minus the present value of the strike, RT, and then we have N D2. So if we wanted to account for the dividends, what you would do is you would correct this price, the stock price here, for that value of the dividend. And so this new stock price would essentially be equal to S0 minus the present value of the dividend, and then you're going to have everything else the same in D1. But remember, D1 is also a function of the dividends, right? So D1 is also going to change in a similar manner, minus the strike price present value, and you have N D2, and D2 is also a function of the strike. So what is D1? D1 is equal to the log of S0, but every time we have X0, we're going to do minus present value of the dividend. We're going to divide that by the strike price plus risk-free plus variance divided by 2 T, and we divide that by standard deviation squared of T. That's going to be our D1, and this is the adjustment that needs to be made with D1. D2 is the same. We're going to change the sign to negative, essentially, for D2. Only dividend with the ex-dividend dates during the life of the option should be exercised. So dividends are declared and will be paid later in the during the dividend during the life of the option would be included here. The dividends should be the expected reduction in the stock price on the expected dividend date. So just why you correct that stock price here for the present value of the dividends. All right, so if we're working with American calls, what do we have? So far we worked with European calls, and we've worked with D1 and D2, and all of that was in under the assumption that the option is held all the way to maturity. With American options, the option may not be held all the way to maturity. So how do we make the correction for that? An American call on a non-dividend paying stock should never be exercised early. Well, that is true. I mean, you remember, I think we talked about that in the previous unit, or you should have read about that in the previous unit. Um, why is that? Why should American call not be exercised early on non-dividend paying stocks? Well, that's because if you have a timeline like this, where this is the maturity of the expiration of the option, and this is when the option is written, and at this point in time here you already have an option that's in the money, so you have ST here that's greater than K. Why would you pay K here for the stock if you know that you would pay K here for the stock anyway, right? The idea here is save the money, save K, invest that at an interest rate, invest at an interest rate, and earn the future value of your interest rate of your strike price over this period of time here, and essentially use the outcome of this investment to pay for the strike price later. So exercising the option means you have to pay the strike price. Why would you pay the strike price now when you can pay it later? That's why you don't want to exercise. At least that's one of the reasons you won't want to exercise the American option early. Another reason you don't want to exercise the American option early, maybe because the option may be in the money. Now, but by the time you get it in, if you exercise, essentially you're paying K for the stock price, for the stock at this point in time. But at expiration, it may just be that the option is out of the money. And so if the option is out of the money, what that means is, if we're talking about a call option here, it means that the stock price, or the stock price, is far less than the strike price. And so if you exercise early, you've paid the strike price, where by waiting you may be paying a value that's much less than the strike price. So you don't want to exercise an American option early. And that's consistent with what the pricing that we've done. And I think we talked about, we looked at the boundaries of European call, and because the American call has a built-in option of being exercised early, the American call is generally more valuable than the European call. So the call premium on the American option is going to be higher than the call premium on the European option. So when you look at the boundary for European call, you're going to have so it's going to be European call less than the American call, and then here you're going to have the lower bound of the European calling, if I remember correctly. That's going to be S0, I think it's plus the present value of the strike. Actually, it's minus the present value of the strike. That's going to be the lower boundary for the American call, and this is the European call, this will be American call. And this is more valuable than that just because of the built-in option of exercising early. Alright. What else do we have here? An American call on the dividend paying stock should only ever be exercised immediately prior to the ex-dividend date. The ex-dividend date, if you remember, is the date at which the company determines who gets paid the dividend, right? So if you hold the stock, this is your ex-dividend date. If you hold the stock before ex-dividend date, you get the dividend. If you hold the stock, if you buy the stock here, you get the dividend. If you buy the stock here, you do not get the dividend. The holder of the seller of the stock gets the dividend here. So if you are to exercise the option, which means that you're buying the stock at the strike price, you should exercise the option before ex-dividend date, and that's what that is all about here. All right, so Fisher Black has done an approximation for dealing with dividends in American option, and we're not going to dig into this, but essentially you would essentially set the American option equal to the maximum of two European prices, where the first European price is for an option that's maturing at the same time as the American option, so they have the same maturity, and the second European option price is for an option that's maturing before the final ex-dividend date of the option. That is to allow for you to be able to exercise before the ex-dividend date in order to acquire the stock. So if you are to if you are to exercise a dividend paying stock, do it before the ex-dividend date. So you set up the second option that you have here is set up to expire right before that ex-dividend date to facilitate or to price the value of the option at that point in time. All right, so this is what we have for this. Before I let you go, I know this is already a long video, so it's an hour and 45 minutes. So it's already a really long video, but we need to squeeze this in order to wrap this up effectively. And so the way we're going to do that is go back to the slides here, and we're going to talk a little bit about the put call parity. And in doing our put call parity, what we want to do is we want to be able to derive essentially our Black-Scholes option pricing value for a put option. And so this is what we have. If you recall your put call parity, it said that a call plus the present value of the strike is equal to the put value plus the stock. That is our Black-Scholes option pricing. And so we know what the call option value, call option price is, and we can essentially solve for the put. So in this case, the put is simply going to be equal to the call minus the present plus the present value of the strike minus the stock. And so if we substitute the values, what are we going to get? We know our call is equal to S0 and ND1, and then here what we have is we have plus the present value of the strike, so it's going to be plus, it's going to be minus here, minus K, and then we're going to have N present value, and we're going to have ND2, and so that's going to be our call option value plus present value of the strike minus S0. Okay, so we get rid of the parentheses. So if we get rid of the parentheses or the brackets that we have there, what do we have? We essentially have the following. We have S0 and D1, and then we do minus S0 here, so that minus S0. So that's gonna be this and that, and then we're gonna have plus K present value minus K present value. So this is that value and this, and then we're gonna have ND2. All right, so in this case we have S0 here, S0 here, so we factor that out. So it's gonna be S0 and D1 minus 1, and we're gonna do plus here, and then we're gonna factor out the present value here, so minus RT, and we're gonna have 1 minus ND2. Alright, so this gives us our put option value, and we can simplify this even further. And the way we're going to go about simplifying this even further is by saying nd1 minus 1, that is also equal to minus 1 minus nd1. And so multiplied by s0, we would have s0 minus, and you would essentially add what we have here, present value of the strike, and then 1 minus nd2. And so the put option value, the traditional definition of put option value, is equal to the strike price, present value, multiplied by 1 minus nd2, and then you subtract s0, that is multiplied this time by 1 minus nd1. Now you remember that D1 and D2 are defined as early log of stock divided by strike, plus risk-free plus 1/2 of variance multiplied by T divided by square root of T multiplied by sigma for D1. And then for D2, we just do log of stock divided by strike, plus risk-free minus 1 over variance multiplied by T divided by square root of T times R times sigma. And so this is going to be our put option value according to Black-Scholes, and given the put call parity. That's our put call parity there, and we have a put option value here. Now usually you also refer to this term here as the delta of the put becomes the negative sign. You know that the delta of the put is always going to be negative. And for the call, you refer to this value here as the delta of the call, and the delta of the call is always going to be positive. And you remember that the delta of a call, delta call plus the delta of a put is equal to 1. So we can have nd1 plus 1 minus nd1, and that's going to be equal to the nd1 are going to cancel each other. It's going to be equal to 1. And that's one of the reasons this is often written in this format rather than this format, although they are identical. Essentially they're the same thing. Usually the reason it's expressed like this is to make it clear that because the sum of the delta is equal to 1, you want to be careful to know that this value here comes with a negative sign, so that the delta of the put is negative. Alright, this is a way too long video. I didn't intend this to be this long, but I kind of wanted to go over the slides here in this video, and that's what we did here. Alright, I'm gonna stop here. That will be it. We're gonna do a couple of practice in the next video, just to go over some of this material, talk about confidence interval, and do option pricing evaluation in the next videos, using binomial essentially. Alright, this wraps this up. I'll see you in the next video.